In this video, we're going to explore continuous time convolution as a way of finding the output by convoluting the input in an impulse response. Since this is continuous time, the convolution will be expressed in terms of a what we call a convolution integrals. So basically, we're going to have and if you haven't seen the definition part of the conversation or the video, you should go back and take a look at that. Assuming you've looked at it, then we know that the convolution integral, which describes the output of a system, is going to be equal to the input of the system convoluted with its transfer function impulse response, which we represent with h of t. Now, the mathematical expression, this is called the convolution for continuous time, so therefore it's going to be a convolution integral, which is going to go from minus infinity to infinity, and here the integration variable would be tau, just to differentiate it from t, because every time you do this integral, t acts as a constant, but you're going to do this for all the possible t, so you're going to have many integrals as you go through. So this will be x of tau and h of t minus tau, representing what happens when you do a convolution. Okay, and d of t basically tells us what the variable of integration is. Great. Now we have a problem here which is asking us to take an input, run it through a system that is defined by h of t, and find out what y of t is. So that's our job. And what we're going to do, we're going to use this. Now when you do a convolution, as we've talked in the introductory video, you can take either a graphical or intuitive approach, which is what we're going to do here, or you can take a mathematical approach, which we're going to do in a future video. But for this case, we're going to take a graphical approach, and we're going to go through it step by step. And the nice thing about graphical approach is that every step of the way you can kind of see how the integration, convolution integral, evolves as you go forward. Since it's a convolution integral is an integral which integrates the product of these two, is basically we're looking for places for any given value of t where both of these are non-zero, because if one of them is 0 and you multiply them, the whole thing goes to 0. Okay, in order for us to see where the non-zero values are, we have to do some work. So the step one we're going to take is we're going to we're actually going to do plot x of tau, which is simply take anywhere you see t and replace tau and solve it. Looking at that, that's a pretty, hopefully, straightforward thing to do. If the axis is here, the zero axis is here, and let's say 2 sits here, since you're multiplying, since x of t is multiplied by this, it basically is saying that this function is going to be basically 0 until it's here, hits 0 on the tau scale. Then it's going to go up to 2, and after 2, since this is e to the minus 5 tau, this is going to decay. Eventually at infinity goes to 0, but it's going to decay at the rate of 2e to the minus 5 tau, and that's cool. So that's our let's bolden the graph a little bit, and here is our x of tau. That was easy, just basically all we did, we replaced t with tau. The second one we have to plot is basically h of t minus tau, remembering that we want to integrate t every different values of t over time, but the variable of integration is tau. This is really kind of important to keep remembering that. So, oops, why is this coming up? Okay, we are back here, and now what we are seeing is that we would need to do this. So we have h of t, so what probably the best thing would be to, on the side, just draw because we eventually want to draw h of tau here. Okay, whoops, let's draw it all the way. Tau here, and we want to kind of do the h of tau on this. But before I do that, I got to figure out what the h of tau is, and I'm going to do a little sketch here as we work our way down. So h of tau, based on this equation, is going to be 4 times u of t minus 2. So it comes up at t larger than 2, and then goes away at t equal to 5, based on the fact that these two are being used. So if I plot this, this is h of tau, basically replacing t with tau. That's all we're doing. And so we're going to have this signal that stays low until 2. At 2 it pops up to magnitude of 4, and then at 5 it goes away and goes. So this is our signal. But we're really not looking for h of t, we're looking for h of tau. We're looking for h of t minus tau. So now we got to do that tau, which means we got to mirror image this around the vertical axis. So what we're going to end up for h of minus tau is minus 5 minus 2. So our signal basically flips. Magnitude still 4. And now, in order for me to create a t minus tau, all I have to do is add t to these two locations, and we're done. So now that we've kind of gone through step A to draw h of tau, then h of minus tau, now we are ready with our final thing of drawing basically the final signal, which is is h of t minus tau. And notice how I'm drawing it all the way to the left, so it kind of become clear kind of where it's going to have an overlap. So, and actually I should have drawn this all, because they go all the way back to 0. So it comes here, pops up, pops back down, and there is my signal. So this happens at t minus 5, this happens at t minus 2. Okay, so step A, step B, and finally step C. Now I've got h of t, and I've got all of that, and I've got h of t minus tau. Now all I have to do at this point is start moving this forward. As you can see, when the front end t minus 2 is less than 0, so t minus 2 is less than 0. So if t minus 2 is less than 0, which basically tells me t is less than 2, that this has not reached where the non-zero of x of t is, which means there's this integral, one of those, in this integral, x of tau is equal to 0. So it really doesn't matter what h of tau is. In this area, the y of t is equal to 0. Okay. Now what I'm going to do, I'm going to see if I can grab this and start moving it. Notice now so now that that's a condition, the next condition is t is larger or equal to 2. So what does that mean? That basically means, let's see if I can grab this and move it. So this now has moved past the 0 point, and now it's inside this area. So if you look at it, let me just use a red pen. If you look at it, there is a bit of an overlap, right? In this specific area, you've got non-zero h of t minus tau and non-zero x of t, which means now in order for me to find y of t, all I have to do is write the integral. And which integral? We're writing this integral. But the limits is going to be, non-zero starts at 0, and you finish it at t minus 2, front end of that. And then, so that is true until t minus 5 arrives in here. So the other side of this is going to be less than 5. Okay, so this was no overlap. the first case. This is a partial overlap because half of them overlapping, half of them don't overlap. And so let's do the next interval. Well, actually, let's finish this one. So 0 to t minus 2, and then the equation is going to be this. Remember, this was 4, the magnitude. So it's going to be 4 for the, well, actually, let's write it in order. The first thing you got to write the x of t. X of t is simply 2e to the minus 5 tau. And h of t minus tau is simply 4. Okay? So to solve this, we're just basically doing an integral. 8 comes out as a constant. This goes 0 to t minus 2, e to the minus 5 tau. When you integrate, that becomes minus 8/5 e to the minus 5 tau. And integration from 0 to t minus 2. And if you want to go further, you can evaluate this. And if you evaluate this, you're going to get minus 8/5 e to the minus 5 t minus 2 and plus, I'm sorry, minus, yeah, plus 0 in here, that makes it a 1, it would be 8/5. And so that is basically the value as long as t is between those two. Now, let's go to the next one. Next one is going to happen when t is larger or equal to 5. That means this edge now has entered. Now the whole h of t minus t is within the other signal. So let's go ahead and see if I still can get this one to move a little more. So this one now, for this case, what has happened is this is moved past that point. So I'm going to erase these two so you can see them. So now what's happening here is that this t minus 5 has passed the 0 point. So the 0 point is over here, and this is inside, this is inside. So this goes on for infinity, basically. You know, it's going to be overlapped till the end of the days. So that basically tells us that my y of t now is going to be integral, but this time the lower end of the integral is going to be t minus 5. The upper end of the integral is going to be t minus 2. The inside the equation is going to be the same. It's 4 times that. So you're still going to have 2e to the minus 5 tau times 4. And that whole thing becomes 8. This time the integration goes from t minus 5 to t minus 2 e to the minus 5 tau. It's very similar, right? It's going to be 8/5 e to the minus 5 tau tau, where the integration limit goes from t minus 5 to t minus 2. So you're going to minus 8/5 e to the minus 5 t minus 2 plus a to the 5th e to the minus 5 t minus 5. Okay? And that's it. We are done. And this is full overlap. And since the x signal in this case goes all the way to infinity, no need to have another intervals, because it's going to be full overlap all the way to infinity. So now if somebody comes to you and says, hey, find me y of t at, let's say, 3 seconds. So let's say they come and tell you find y of 3. You say that's really easy. 3 is in this interval, so I can use this equation. And you simply say, okay, that means t is equal to 3. So t equal to 3, that's what you want. So it's going to be 8/5. I'm going to use this because that's the interval I'm in. 8/5 e to the minus 5, 3 minus 1, minus 2, plus 8/5. And that'll take care of it. You can resolve that. I mean, so we can clean it just a touch more. We can take the 8/5, take it all out. It's going to be 1 minus e to the minus 5. And that's the answer. And that brings us to an end of an example of applying a graphical approach. And you notice that you got all your y's for all possible values of t, and you're able to find your output of this system using convolution and using a graphical or intuitive in a continuous time.